Welcome to this problem walkthrough. Today, we'll explore LeetCode problem number 1593, split a string into the max number of unique substrings. In this problem, we'll work on splitting a string to maximize the number of unique substrings. Stick around as we break this down step by step and discuss various approaches to tackle the challenge effectively. In this problem, you're given a string S and tasked with splitting it into the maximum number of unique substrings. The goal is to determine how many unique substrings you can obtain by splitting the string. A substring is simply a sequence of one or more contiguous characters from the string. For instance, in the string ABC, possible substrings include a, B, C, UB, BC, and ABC. To solve the problem, you need to ensure that all substrings from your split are unique, and then return the maximum count of such unique substrings. The input is a single string S, and the output is an integer representing this maximum count. Let's look at an example. Consider the input string S equals ABAP. One valid way to split this string is into substrings of B, UB, C, and CC. Each of these substrings is unique, and there are 5 of them in total. While there may be other ways to split the string, the maximum possible count of unique substrings is 5. Next, take the input string S equals ABA. For the string S equals ABA, one way to split it is into a NBA, which gives 2 unique substrings. Alternatively, you could split it as UB and A. Both of these approaches result in 2 unique substrings, which is the maximum possible count. Now, consider the input string S equals AA. For the string S equals AA, the only valid split is the entire string itself, AA. If you try to split it into a and A, the substrings would no longer be unique, as both are identical. Therefore, the maximum number of unique substrings for this string is 1. The problem comes with constraints to guide your approach. The string length is at most 16 characters, which allows for exhaustive methods like backtracking. It's important to remember that substrings must be contiguous, and no 2 substrings in a split can be identical. Edge cases include strings with a single character, which always result in an output of 1, or strings with completely unique characters, where the output equals the string length. To tackle the problem of splitting a string into the maximum number of unique substrings, we considered 2 main approaches. The first is the brute force approach, which involves generating all possible ways to split the string and counting the unique substrings in each split. This method uses recursion to explore every possible split point, while a set is used to ensure substrings are unique. However, the computational complexity of this approach is exponential, specifically 2 to the power of n*n, since there are 2 n1 ways to split a string of length n, and each split requires checking for uniqueness. This makes brute force impractical for large inputs. Next, we have backtracking with a set, which is a more structured approach. Here, backtracking is used to explore all potential substrings while ensuring uniqueness by maintaining a set. At each step, we can either extend the current substring or start a new one. Although this approach is still exponential in complexity, it introduces pruning by skipping invalid paths, making it more efficient than brute force. However, it still struggles with high computational costs for very large strings, highlighting the need for further optimization. Building on the backtracking approach, we consider an optimized version that incorporates additional strategies to improve efficiency. This version uses pruning techniques to terminate paths early when further exploration cannot improve the current maximum count of unique substrings. For example, if the remaining portion of the string is too short to yield enough new unique substrings to exceed our current maximum, we can stop exploring that path. This optimization reduces redundant computations significantly. The implementation still relies on backtracking, with a set to enforce uniqueness, but now includes mechanisms to track the maximum achievable count and skip unnecessary splits. While the worst-case complexity remains exponential, the average-case performance is greatly improved thanks to these optimizations. Ultimately, this approach strikes a balance between exploring all possible splits and ensuring efficiency by focusing computational effort where it matters most. This makes optimized backtracking the chosen strategy for this problem. Optimized backtracking stands out as the most practical approach because it provides the best trade-off between correctness and efficiency. While dynamic programming might seem like an alternative, adapting it to enforce the uniqueness constraint without introducing excessive overhead is highly challenging. Brute force, on the other hand, guarantees accuracy but is computationally prohibitive due to its exponential complexity. Naive backtracking is an improvement over brute force but lacks the necessary pruning optimizations to handle larger inputs effectively. With optimized backtracking, we can enforce the uniqueness constraint naturally using a set, and the recursive exploration of substrings aligns well with the problem's requirements. Additionally, pruning invalid paths and terminating early when further exploration is futile significantly enhances performance. While backtracking remains exponential in the worst case, it offers a balanced approach that combines thorough exploration with reduced redundancy. In conclusion, this method achieves a strong balance of correctness and efficiency, making it the most suitable solution for this problem. The problem we're tackling here is to split a string into the maximum number of unique substrings. A substring is simply a contiguous sequence of characters within the string. The challenge is to ensure that all substrings in your split are distinct, and the goal is to maximize the number of these unique substrings. To achieve this, we use a backtracking approach, which systematically explores all possible ways to split the string. First, we define a helper function called backtrack that takes two parameters, start, which indicates the index in the string where we begin exploring substrings, and scene, a set that tracks all unique substrings added so far. The function's purpose is to return the maximum number of unique substrings that can be formed starting from the given index. The base case for this function is straightforward. If start equals the length of the string, meaning we've processed the entire string, we simply return the size of the scene set, which tells us how many unique substrings have been found so far. To handle the recursive case, we initialize a variable max_count to 0. This variable keeps track of the maximum number of unique substrings encountered during our exploration. We then iterate through all potential substrings starting from the start index. For each n index from start plus 1 to the length of the string plus 1, we extract the substring sub from s, start end. If this substring is not already in the scene set, we know it's unique. In that case, we add sub to the scene set and make a recursive call to backtrack, starting at the end index. This allows us to explore further splits beyond the current substring. After the recursive call, we update max_count with the maximum value between its current value and the result of the recursive call. Finally, to backtrack and try other possibilities, we remove sub from the scene set. Once all substrings have been explored, the function returns max_count. To initiate this process, we call backtrack with the starting index of 0 and an empty scene set. This approach works because backtracking enables us to exhaustively search all possible ways to split the string. By iterating through every potential substring start and endpoint, we ensure that no valid splitting option is overlooked. The scene set plays a crucial role in pruning the search space by enforcing the uniqueness of substrings. This prevents redundant computations and ensures correctness. Additionally, the algorithm includes an early termination mechanism. If adding a new substring would violate the uniqueness constraint, we immediately stop exploring that branch, saving computational resources. Another optimization is skipping duplicates. If a candidate substring has already been added to the scene set, we bypass it entirely, reducing unnecessary recursive calls. Together, these insights make the algorithm both effective and efficient. To implement this solution, we rely on key data structures. First, the scene set is used to keep track of substrings that have already been added in the current split, ensuring that every substring remains unique. Second, the recursive call stack is implicitly used to explore different branches of the solution space. The depth of this stack corresponds to the number of characters in the string. In terms of complexity, the time complexity in the worst case is 2 to the power of n, since every character can either start a new substring or be part of the previous one, leading to an exponential number of splits. However, the pruning mechanism significantly reduces this complexity in practice. Space complexity is determined by the scene set, which requires n space in the worst case when all characters are unique, and the recursive call stack, which also goes up to a depth of n. To illustrate how the algorithm works, let's consider the string s equals abap. We start with an empty scene set and begin exploring substrings from the first character. For example, we can add a to the scene set and recursively process the rest of the string. Alternatively, we can add aba, and so on, exploring all possible splits. At each step, we backtrack and try other options to ensure we find the maximum number of unique substrings. For this input, one optimal split is A, B, B, C, 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 which gives us 5 unique substrings. This example demonstrates how backtracking allows us to explore all possibilities while the scene set ensures uniqueness and prevents redundant computations. Overall, the algorithm guarantees an optimal solution by leveraging the systematic exploration provided by backtracking and the efficiency of pruning. This solution uses a backtracking approach to maximize the number of unique substrings we can extract from the input string S. The key idea is to systematically try all possible ways to split the string and track the substrings we've already used. Here's how the code works. First, we define the max unique split function, which takes the string S as input. Inside, we define a helper function backtrack that handles the recursive exploration of substrings. The backtrack function takes 2 arguments, index, representing the current position in the string, and scene, a set that keeps track of substrings already used. The recursion stops when index reaches the end of the string, base case. At that point, the function returns the size of the scene set, which represents the number of unique substrings. The recursive process involves iterating through all possible substrings starting at the current index. For each substring, we check if it's already in scene. If it's not, we add it to scene and recursively call backtrack with the next starting position. After the recursive call, we backtrack by removing the substring from scene, ensuring that other recursive paths remain unaffected. The max_count variable keeps track of the maximum number of unique substrings found across all recursive paths. Finally, the top-level call to backtrack starts the process with an empty set in index 0, and the result of the function is returned. This approach ensures that we explore all possible splits of the string and track the maximum number of unique substrings. The complexity of the solution is exponential due to the recursive exploration, but it is efficient for the given constraints of the problem. Here, we start by defining a Java solution that uses backtracking to solve the problem of splitting a string into the maximum number of unique substrings. The main method, maxUniqueSplit, takes the input string S and calls the helper function backtrack. This helper function is designed to recursively explore all possible ways to split the string while keeping track of unique substrings using a hash set called scene. The base case for the recursion is when the index reaches the length of the string, meaning we've processed the entire string. At that point, the size of the scene set, which contains all the unique substrings, is returned. The maxCount variable is used to track the maximum number of unique substrings we can achieve as we iterate through possible splits starting from the current index. A for loop is used to generate all substrings starting at the current index, and we check if each substring is unique by verifying that it is not already in the scene set. If it is unique, we add it to the set, make a recursive call to continue processing the rest of the string, and then backtrack by removing the substring from the set. This process ensures that we explore all possible combinations of unique splits. Finally, we close the class definition, wrapping up our solution. The recursion systematically evaluates all potential splits, and the use of the scene set guarantees that we only consider unique substrings. By leveraging backtracking, this approach ensures we explore every valid possibility while reverting changes during the backtracking step to maintain correctness. The solution efficiently balances the need to maximize unique substrings with the constraints of the input string, providing an optimal result for this problem. Let's start by examining example 1, where the input string is ABAC. Initially, we begin at index 0 with an empty set called scene. The goal here is to split the string into as many unique substrings as possible. Starting from index 0, we first try the substring A, which is the first character of the string. Since it is not in the scene set, we add it and then make a recursive call to explore the rest of the string from index 1, now with scene containing A. Next, from index 1, we test the substring B. Again, B is unique, so we add it to scene, which now becomes A, B, and continue exploring from index 2. The process repeats recursively as we attempt to form new substrings while ensuring they are unique. At index 2, when we test the substring A, we notice that it already exists in the scene set, so we skip it and move on. Instead, we try the substring AB, which spans from index 2 to 4. Since AB is new, we add it to scene, making it A, B, AB, and continue recursively from index 4. The process of exploring unique substrings continues, with the algorithm adding each newly discovered unique substring to the scene set while backtracking after each recursive call to evaluate other possibilities. Eventually, we find that the maximum set of unique substrings we can form is a B, a B, C, C, which contains 5 elements. Therefore, the result for this example is 5. In example 2, the input string is AAAA. As before, we start at index 0 with an empty scene set. The first substring we attempt is a, which is unique, so we add it to scene and proceed recursively from index 1. At index 1, we test the substring in again, but since it is already in scene, we skip it. Next, we try the substring AA, which is unique, so we add it to scene, making it a AA, and continue recursively from index 3. The process of exploring substrings and backtracking continues as we attempt to form new unique substrings while ensuring no duplicates are added. After exhausting all possibilities, we find that no additional unique substrings can be formed beyond a AA. Thus, the total number of unique substrings for this example is 2. Now let's consider example 3, where the input string is ABCDEF. Starting at index 0, we attempt substrings sequentially, a, B, C, D, E, and F. Since all characters in this string are unique and do not repeat, we add each one directly to the scene set. The scene set eventually contains a, B, C, D, E, F. Finally, for example 3, we find that all 6 substrings are unique, resulting in a total of 6. Summarizing the results for all examples, for the input ABAP, the maximum number of unique substrings is 5, for AAA, it is 2, and for ABCDF, it is 6. These results highlight how the algorithm dynamically explores substrings and leverages recursive backtracking to ensure the maximum possible number of unique substrings is identified for each input. To analyze the time complexity, let's first consider how the algorithm explores all possible partitions of the string using backtracking. If we denote the length of the string as n, the recursive tree depth can extend up to n because, in the worst case, the algorithm might need to make decisions at every index of the string. At each recursive level, the function determines how many characters to include in the current substring, ranging from 1 to the remaining characters, which is n index. This means that at every step, there are up to n index recursive calls. Since the decisions we make ripple through all possible ways to split the string, the total number of recursive calls can grow exponentially, approximately reaching 2n in the worst case. Each recursive call involves checking whether a substring is in the scene set, which is a constant time operation on average. This exponential growth in the number of function calls is what defines the time complexity in such cases. Now, taking the worst-case scenario into account, the exponential growth of recursive calls means the time complexity is 2 to the power of n. While there are cases where the recursion exits early, for example, if the string cannot be split into many unique substrings, these cases are relatively rare and do not change the dominant exponential nature of the problem. On the other hand, the space complexity originates from 2 main factors: the recursive call stack and the scene set used to track substrings. The recursion depth corresponds directly to the length of the string n, meaning the call stack uses n space. This is because, at most, the algorithm will have one recursive call for each character in the string as it progresses deeper into the recursion. In addition to the call stack, the scene set introduces further space requirements. This set keeps track of all substrings encountered during recursion. In the worst case, where every character forms its own unique substring, the scene set would contain n substrings. The total size of these substrings is proportional to the sum of their lengths, which follows the formula 1 plus 2 plus 3 plus n, resulting in a total size of n asterisk, n plus 1/2. This gives a worst-case space requirement of n squared for storing substrings. Combining this with the recursive call stack, the overall worst-case space complexity becomes n squared. When analyzing different scenarios, the best case occurs when the string has very few unique characters, causing the recursion to terminate early. Here, the time complexity is closer to n, and the space complexity is also reduced to n. However, in average and worst-case scenarios, the time complexity approaches 2 to the power of n, and the space complexity remains n squared. Finally, let's compare this backtracking approach to a brute force method. A brute force solution would involve generating all possible partitions of the string and then checking each partition for uniqueness. While this would also have exponential complexity, it is far less efficient due to redundant checks and unnecessary computation. In contrast, the backtracking approach optimizes the process by maintaining a scene set to avoid exploring already invalid paths. Despite this optimization, the problem's exponential nature remains unchanged, as the number of recursive branches still grows exponentially. From a mathematical perspective, the time complexity of O2 to the power of n arises because the recursion is effectively exploring the power set of the n characters in the string, and the size of the power set is 2n. For space complexity, the scene set contributes up to O(n) squared in the worst case, while the recursive call stack adds another O(n). Together, these factors confirm an overall space complexity of O(n) squared. When tackling this problem, there are a few common mistakes to watch out for. First, not properly handling duplicate substrings is a frequent issue. Beginners might forget that all substrings in the split must be unique, which violates the problem's constraints. To avoid this, consistently use a set to track substrings as you build solutions. Next, skipping edge cases can lead to incorrect results. For example, strings like AAAA, where all characters are the same, or very short strings like AB need special attention. Your solution must handle scenarios where substrings are identical or the string is too short to split further. Another pitfall is inefficient backtracking. Without pruning invalid paths such as those leading to duplicate substrings, you may waste time exploring unnecessary branches. Always terminate these paths early using your set to validate each step. Lastly, a misunderstanding of the constraint to maximize the number of unique substrings can lead to focusing on length instead of count. Remember, the goal is to maximize the count of unique substrings, even if they are as short as a single character. A poor choice of base cases in recursion is another mistake to avoid. If you don't properly handle the termination condition in your recursive function, you risk infinite loops or incomplete solutions. Make sure to end the recursion when the entire string has been processed. Now, in interviews, this problem is an excellent opportunity to demonstrate your understanding of backtracking. The key idea is to explore all possible string splits while ensuring substrings are unique. Interviewers may also ask about efficiency versus completeness. You should be ready to explain how a brute force approach works and compare it to optimized solutions that use pruning to reduce unnecessary computations. Additionally, highlight your ability to generalize this strategy to other problems involving unique subsets or combinations, as this is a valuable skill that interviewers often test. Finally, being able to discuss how your solution handles edge cases, such as strings with repeating characters, very short lengths, or even strings that can't be split further, shows a thorough understanding of the problem. To build connections, it's helpful to see how this problem relates to others. For instance, LeetCode 46, permutations, involves using backtracking to generate all possible permutations of a sequence. Similarly, LeetCode 93, restore IP addresses, is another string splitting problem, but with additional constraints for valid IP formatting. LeetCode 131, palindrome partitioning, focuses on splitting a string into valid palindrome partitions, and LeetCode 140, word break 2, requires recursive splitting while validating against a dictionary. Now, considering alternative approaches, the simplest method is brute force. This involves generating all possible splits of the string and checking if the substrings are unique. While this guarantees correctness, its time complexity of O2 to the power of n makes it impractical for larger inputs. A more efficient method is optimized backtracking. By using recursion alongside a set to maintain unique substrings and pruning invalid paths, this approach achieves a balance between performance and simplicity. Though still exponential, the pruning makes it much faster and more scalable than brute force. Another approach, though rarely used, is dynamic programming. Here, you track the maximum number of unique substrings for each prefix of the string. While its complexity, O(n) squared, is better than backtracking in some cases, it comes with trade-offs. Dynamic programming solutions are less intuitive and harder to implement cleanly, especially under interview constraints where clarity and explanation matter. Additionally, it may not align as naturally with the problem's recursive nature, making it a less common choice for this specific challenge. Overall, while dynamic programming can be an alternative, optimized backtracking is usually the preferred method due to its balance of efficiency, clarity, and alignment with the problem's requirements. By mastering these approaches, you can confidently handle variations of this problem and others with similar constraints. Great job following through. To wrap up, we used a backtracking approach to split the string into the maximum number of unique substrings. This problem is a great example of leveraging recursion and state management. Thanks for watching, and we hope to see you in the next tutorial. Keep coding and stay curious. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!